What are initial conditions? Show the behavior of R, L and C elements at the time of switching. The initial condition of an RLC circuit is the state of the circuit before a switching operation, that is before closing or opening of the switch. It is the values of the current and voltage across the elements. Here element means it may be a resistor or inductor or capacitor of the circuit at that instant. Let me give an example. Suppose say this is a circuit having RLC element connected to a supply voltage like this. This is R, L and C. Here let me assume this as a switch, and I'll assume that at t equal to 0 the switch will be closed. So this is RLC circuit with switch. It indicates that at t equal to 0 switch will be closed. Here we can observe that before t equal to 0 the switch was opened. So when switch was opened, the current in the inductor or voltage across the capacitor is known as initial values or initial conditions of the circuit. Now let's see, show the behavior of R, L and C elements at the time of switching. Here the time of switching means it may be a opening of the switch or it may be a closing of the switch. So here let me take the three columns. One indicates the elements, another one is behavior immediately after switching operation and behavior at a steady state. Here immediately after switching operation means we'll consider it as t equal to 0 plus. Behavior at steady state. Steady state means after a long time the circuit will be settled. We'll take that period as t equal to infinity. Let me take the first element as resistor. Say this is a resistor. So in RLC circuit with switch, the behavior immediately after switching operation, that is at t equal to 0 plus, the behavior of the resistor will be same. That is the behavior of the resistor will be same. There is no any changes in the resistor. Similarly, at t equal to infinity, the behavior of the resistor will be same. That is behavior of the resistor is independent of time. Suppose if I consider the inductor, behavior of the inductor at t equal to 0 plus. So at t equal to 0 plus, inductor acts like open circuit. So this is acts like open circuit. So here it is open, it means the inductor is removed, it means it acts as an open circuit. Similarly, at a steady state, that is at t equal to infinity, inductor acts like short circuit. So this inductor is replaced by short circuit. This is short circuit. Suppose this is terminal A and this is terminal B. So this will be open circuit and here it will be short circuit between A and B. Now let me assume there is an inductor and let me assume the initial current in the inductor is I0. So if before switching operation, if initial current in the inductor is I0, then immediately at t equal to 0 plus, inductor acts like current source. That is, the inductor acts like current source between the same terminal A and B. So this is the current source with magnitude I0. Similarly, at t equal to infinity, it can be represented as, that is, this is I0, this is A terminal and this is B terminal. Now let me consider a capacitor. Assume that capacitor is connected between terminal A and B. So the behavior of the capacitor at switching operation, that is at t equal to 0 plus, capacitor acts like short circuit. So capacitor acts like short circuit, which can be shown as short circuit. This is between terminal A and B. Similarly, at t equal to infinity, capacitor acts like open circuit. So this is acts like open circuit. This is A and this is B. Now let me assume that there exists some voltage across the capacitor before switching operation. That is, let me assume voltage across capacitor is V0 before switching operation. So in that case, at t equal to 0 plus, capacitor acts like voltage source. Capacitor acts like voltage source of magnitude V0 plus minus, that is magnitude V0. Similarly, at t equal to infinity, it acts like again open circuit. It can be shown as, here we have a voltage source and this will be open circuit. This is terminal A and this is terminal B. So this is the behavior of RLC at t equal to 0 plus and at t equal to infinity. Thank you for watching.